Forrest Breyfogle here. In this session, I'll describe how to create metric reports that lead to the best behaviors. Organizations have an elephant in the room issue that is typically not discussed. That issue is scorecard reporting. Scorecard reports should lead to the best actions or non-actions in an organization, but often that does not occur. This session will describe the issues with commonplace traditional metric reporting and what to do to resolve this issue so that the best behaviors occur because of these reports. I will use the time it takes for someone to commute from home to work to illustrate the benefits of an alternative metric reporting approach. Consider the time it takes for someone to commute from home to work by way of car. The time to travel would not be precisely the same every day because commute time is a function of the amount of traffic encountered and delays from traffic signals, among other things. Mathematically, this relationship is y is a function of x, where y is commute time and x's are the inputs to the process, for example, amount of traffic and traffic signals delays. A commuter tracked her commute time for several weeks and observed that typically it takes 25 to 35 minutes to commute. One could consider this commute time variation noise within her commute from home to work process time. When collecting daily commute times, our commuter noticed two unusually long commute times. These two commute times took over an hour, much longer than her typically 25 to 35 minutes commute time. A significant traffic accident caused one commute delay, and in the other situation, the travel delay occurred because of a snowstorm. From a data analysis point of view, we can talk about the specifics of exceptionally long commute times, for example, major traffic accident and inclement weather. However, when we want to understand and give focus to our typical commute time, we should remove these abnormalities points from our metrics tracking. When removing these atypical events, one should not talk about the specifics of what occurred on a particular day within the 25 to 35 typical commute time responses. Discussing the particulars of any noise data point in a process response can lead to erroneous conclusions and inappropriate actions relative to improving the magnitude of a process output response. This commuter wanted to reduce her commute time, and she set a goal for her commute, similar to the measured goal-setting approach used in the company where she is employed. Her goal was to commute time to be no longer than 33 minutes, as shown in the line in the figure. With this metric reporting approach, if a commute time exceeded 33 minutes, she would try to determine what happened during the commute and decide what to do so this problem commute time would not happen again. However, as previously stated, one should not focus on attempting to understand the specifics of what occurred for a specific process response noise data point. This metric reporting approach can lead to much organizational firefighting and wasted efforts that can even be destructive. Our commuter goal-setting approach for her home-to-work commute is similar to organizations using red, yellow, green scorecards to monitor the output response from processes. For this metric tracking approach, a red color triggers action for the scorecard approach because a specific data point did not meet a goal. Red and yellow and green scorecards and similar goal tracking methods for data points can lead to firefighting noise variation or abnormal occurrences, resulting in much organizational waste and even destructive behaviors. In the 80s, Edwards Deming highlighted problems with this commonplace meet the numbers goal management approach in workshops using the red bead experiment exercise. The issues described by Deming in his workshop exercise are no different than those of red, yellow, green scorecards. A 30,000 foot level report format addresses this significant issues where unusual events are separated for typical noise of the process response. In addition, with 30,000 foot level reporting, variation in the output's response is included in the report outs. I'll next illustrate the tracking of our commuter's commute time using a 30,000 foot level approach. This 30,000 foot level report for the commuter time has three components. The first component is the individual's plot, that's the left graph, is for assessing a measure response from stability from a high level point of view, that is a 30,000 foot level view, not unlike a Windows view perspective from an airplane in flight of the terrain below. The mathematics for creating this chart is the same as that of a statistical process controller, SPC, individual's control chart. However, the primary use of an individual's chart is entirely different in a 30,000 foot level report application. With 30,000 foot level reporting, one is not attempting to control a process by identifying special cause signals for resolutions. With 30,000 foot level reporting, the individual's chart only assesses whether a process is stable or not from a high level vantage point. Suppose there are no points beyond the data calculated UCL or upper control limit and LCL lower control limit lines. In that case, the process is considered stable and predictable from this high level perspective. 2. The probability plot right graph is the plot of the data from the individual's chart. Now, if a recent region of process stability measurements is stable / predictable, the data for creating this plot is considered a random sample of the future responses. This prediction statement assumes the future process inputs will be similar to those in the past. The third item this 30,000 foot level report provides is a statement at the bottom of the chart which addresses process stability and predictability. If the process is considered stable, a prediction statement is determined from the probability plot and provided in this statement. This figure shows a commute time that is not stable because of the two abnormal commute times caused by a major traffic accident and snowstorm. Since we want to reduce commute time under normal conditions and have identified the cause for these atypical responses, we can remove these two data points from our chart to create a typical commute response time. From this individual's chart in the 30,000 foot level report, one observes that the process is now considered stable, hence the process is predictable. The bottom of the 30,000 foot level report statement is that her current commute approach has an estimated mean response of about 30 minutes with 80% or 4 out of 5 commute times between 25 and 34 minutes. In this illustration, our commuter selected a process improvement to commute where she departed home a half an hour earlier than what she did previously. This woman thought that this was an X that could affect the overall commute time in addition to the traffic and signal delays that she might incur for any given day. This 30,000 foot commute time chart indicates both the times before and after her change in her home departure times. This figure shows a staging of the individual's chart where our commuter's new process began. The probability plot uses only data from the recent region of stability to create the graph and provide the predictive statement details at the bottom of the chart report. Our commuter's new process departing half an hour earlier provided an estimated mean commute time of about 20 minutes with 4 out of 5 or 80% between 19 and 22 minutes. This mean commute time is much shorter and with less amount of variation than her past processes for not departing earlier, which had an estimated mean commute time of 30 minutes and with 4 out of 5 commute times or 80% between 25 and 34 minutes. Traditional metric reporting often encourages reacting to the ups and downs of commonplace noise responses, leading to much organizational waste and even destructive behaviors. 30,000-foot level reporting provides a high-level process output response perspective that encourages process improvement thinking when needed to improve an overall metrics response. This is your choice. Do you think it is best that your organization continue with scorecards that treat each individual data point as something to react to or not, as described in this home to work commute presentation's illustration? Or do you want to show the output of process with its process output variation so that the most appropriate action or not action occurs? Often it is said that 30,000-foot level reporting is too complex for leadership and others to understand. I suggest that 30,000-foot level reporting is easier to understand. With 30,000-foot level reporting, the statement at the bottom of the chart can provide a predictive statement that includes process variation where, if this statement is undesirable, process improvement and ease is needed. What can be easier to understand? If you think that 30,000-foot level reporting could be a great thing for your organization, but are concerned that others will not buy into the concept, the problem then becomes how to advocacy sell the consideration of 30,000-foot level reporting in an organization. One good place to start is to select a KPI metric that is important to the business, compile data for this metric over time, and create a 30,000-foot level report for the data using our free app. When comparing to a traditional metric reporting approach, it is almost a 100% guarantee that one will gain insight to processes that has never been seen before, which can be very beneficial to improve the KPI future response. The results from metric reporting comparison can then be used to advocacy sell 30,000-foot level reporting considerations in your organization.